All right, so you're asking about 30 and 34 in chapter 3. Okay.
Yeah,
So,
and I know how to do them. I just don't know when to consider the initial velocity of y is zero or the final velocity, if you see what I mean.
in neither of these problems is initial velocity 0, right? So, if in number 30 we're looking at a rugby player. Um, so they're throwing a ball in presumably a parabolic arc, right? Because we're asked to find the angle. And in 34, it's basically the same problem, except it's an arrow that we're firing instead of throwing a rugby ball. Right? So in both of these cases, um, so something we have to be careful with is what period of time we are considering. So say here's an archer from problem 34. It's either an archer or a harpist. I can't decide. Um, so we could say, well, our initial time will be when the arrow is knocked and the archer is aiming, right? Or we could say, no, wait, our initial time is right after the arrow has fired, but before it's really gone anywhere, right? And which of these two choices is more helpful?
Mute. I was muted.
Oh,
Sorry. I was gonna tell you I can't see your what you're
oh
sketching.
yeah. Uh, there we go.
Well, that's the thing. That's the thing that confuses me because for projectile problems, I always thought that we assume the initial to be zero, but I'm wrong. So we have to consider the other system in terms of the final velocity is zero just for the y component, right? When it drops.
Is it? So in the arrow example, we're asked to consider that the archer hit this target on top of a cliff. Right? So, oh, sorry, not that it's 4 meters tall, but that it lands 4 seconds later. So why would we? So we got light blue and dark blue. If we consider light blue to be our starting position, which is where no shot has been taken yet, then the speed of the arrow is 0, right? But what happens between these two instants here?
Arrows fired, and there is velocity.
Yes. So there's so when the archer is holding the arrow on the bow, here acceleration is 0, right? In this middle part, as it's firing, the bow is accelerating the arrow into motion, right? So our acceleration is, say 1, and we'll say this is 1.5, is something in the x direction, right? And then at this point here, the bow has done its work, and the acceleration is just gravity. Okay. So when we brought up our kinematic equations, what is the requirement we have to be able to use our kinematics? What has to be true about acceleration?
We usually use the y component because the zero would cancel out like a whole section, right, of the equation.
So that's just usually, but what's required though? What has to be true before we can use our kinematic equations at all?
In two dimension or
Mm.
just in general?
In general, something has to be true about the acceleration.
That it can't be zero?
It can definitely be zero. Ah, Yusuf's got it. It has to be constant.
Mm.
But if we start in the light blue situation, we've gone through 3 different values of acceleration by the time we fire the arrow, right? So that's definitely not a constant acceleration. So our kinematic equations can't handle that.
I see. I get it now. I didn't know that the acceleration has to be constant.
Mm-hmm. So the reason why we might say that the dark blue situation is our time zero is because then all the way to the target, the acceleration's constant. It's just minus g in the y direction.
And then for this one, we still have to break it down to x and y components, right?
We sure do. They tell us that, let's see, it's 60 degrees above the horizontal with a speed of 30 meters per second. So our initial velocity. All right. So let me clean up some of this stuff so we can have some room. Okay. So our initial speed is 30 meters a second. And we're told that the angle is 60 degrees. And also let me snip the problem, copy it over here. Okay. So let's emphasize the method that we use for going after these problems, right? We always start with as good a picture as we can draw. We follow it up by specifying our coordinate system. So what seems natural to me for this problem is to say that to the right is the positive x direction and that up is the positive y direction. I'm also going to specify that the origin is the spot on the ground right below the arrow when it's fired. Okay, so then step 3 is always break down vectors, always. When we're doing kinematics, there's 4 vectors that are of particular importance to us. And those are the initial position, the final position, the initial velocity, and the acceleration. Initial position we just defined as the point 0, 1.5. Final position we don't know. It's actually what we're looking for in part A. Initial velocity. Okay, do our usual breakdown. The x leg of this triangle here is adjacent to the 60-degree angle. So we'll have a cosine 60, and in the y direction will be sine. Okay. Yusuf asks, what about final velocity? Usually we don't care too much. Now in this one, the part C does ask about final velocity, but if we have all these other things, we can always pull out kinematic 2 or kinematic 3 and get our final velocity. Okay. All right. Jolene, did you want to go through the rest of this problem, or are you satisfied?
I'm good actually. So all we have to do after this is just use the kinematic for the x component and for the y component, right?
Yep. That'll get
Yeah.
us A. B, we have to be a little clever. So for A is kind of the easy part. We use kinematic 1, and we write down, x equals 30 cosine 60t, and y equals 1.5 plus 30 sine 60t minus 5t squared. So that's a system of equations right there. We've got, actually, this is an easy solve, right? Because we have t. So we just plug in t, we get our values. Part B, we have to be a little clever, because they ask, what is the maximum height reached by the arrow along its trajectory? So how do we go after that? Do you have an idea?
Don't we just add the y component to 1.5 to get the whole height?
That's how we get the final height. Right?
So what we just calculated, that would not be the height. That would just be the velocity,
Well,
right?
no, that would be the final. That's the final height, right? That's our y here. What part B is asking? Suppose the arrow does a trajectory like this, right, and it hits the target on the way down. What's the height up here? At the very top of the arc.
That's when we assume that the velocity is 0 in the y component, right? Because it stops for a second, or...
Yeah, that's exactly right. Yeah, so if we're at the top, the y velocity will briefly be 0, right? Because if the y velocity were positive, we'd still be on the way up, so we're not at the top. And if the y velocity is negative, that means we already passed the top and we're on our way down. So yeah, y velocity's got to be 0 at the top. And for that, we can pull out k2. Right? This gives us the time for the height of the trajectory. And then once we have the time for the height of the trajectory, maybe we'll call this TB, because we're on part B. then our max height will be given by k1. So Yusuf says height equals v naught y squared to... Yeah, so I want you to try and break the habit of looking for a special formula in the chapter for situations like this. Like that, quote unquote special formula is really just K1 and K2 put together in the way that we've just put them together here. So there's not some special bit of physics going on here. It's totally normal kinematic physics, and we don't need anything special to deal with it. Does that make sense?
I think I see what Yusuf means. I feel like physics is the only science I've encountered that you don't just have a formula and you just plug in and you're good.
Right.
You really need to dissect it, and I think that's why we all have that habit of just finding an equation, and it's hard to get into this. But I'm sure we'll be able to.
It's because you took chemistry first, right? And in
Yeah.
chemistry, there's 20,000 little laws for every specific situation, right? And then you get to physics, and you're like, nah, it's 3 equations for basically the whole universe. And
True. Thank you for that question. I'm going to give other people a chance, and then I'll fire my other questions.
okay.
Could we go over 4.6, question 27?
You bet.
Thank you.
So let's see. Chapter 4, number 27. Yeah, Selena, I'm totally recording. So it's going to be up on YouTube when we're done. Alright. This is the problem that you were asking for?
Yes, that one.
Okay. Alright, so we've got a bit of a novel here. Freight train's got 2 engines and 45 cars. Alright, so it might take me a second to draw this. Alright, there's one engine. There's 2 engines. And we're not going to draw all the cars. That seems like a lot. But I will draw like the first one. And then we'll do some dot dot dots. And then this will be car 37, car 38, dot dot dot, car 45. Alright, so this problem is a really good exercise in how to split up our system for like maximum efficiency. So first of all, what force must the engines exert in order to accelerate the train forward, right? If the total force of friction is this number and the acceleration is this number. So what I'm going to do for part A is actually draw a separate picture, right? So everything, we're considering everything at once, right? So if this box represents the entire train, then we're going to be pulled forward by the two engines. We are going to be slowed down by the friction, and then of course there will be normal force and mass, and the mass will be 2 engine masses and 45 car masses. And we'll call this positive x and positive y directions. All right. We pull out Newton's second law, right? Oh, did you have a question?
So I noticed that they said like the force is going backwards. So like when I do my thing, I just put like the friction going forward and then the force like with that arrow going backwards. Would that be wrong?
Well, so there's an interesting, like you've got to be a little careful about what we mean by direction. So what they said is the force that the engine exerts on the track, right? So Newton's third law says that the force of the engines on the track has to be equal and opposite to the force of the tracks on the engine, right? And it's the force of the tracks on the engine that's actually moving the train forward. So
Okay.
so if the engines are pushing on the track backwards, but that means the track is pushing on the train forward.
Okay, so like whenever we have like friction ball, it's always gonna be like the back arrow.
Yes, we have to be careful about what friction we mean, right? Because after all, if you think about what direction your car tires turn, right? So when you're driving, yeah, that's exactly right. At the point where they hit the road, your tires are actually moving backwards. And yet they propel your car forward due to Newton's third law, because the force of your tires on the road is equal and opposite to the force of the road on the tires.
Thank you.
All right, so we pull out Newton's second law in the x direction. Chapter 5 is my favorite. It's pretty good. All right, sum of forces. Here's the forces that we actually have in the x direction. And then we have to say, well, that's equal to ma. So we can solve for E. And and this looks ugly, except we actually know all of these values. So acceleration is 0.05. And then the mass of the engines is 8 times 10 to the 4. So 2 of those, and we get 1.6 times 10 to the 5. And then we get 45 of the car masses. add on what they give us for the frictional force. And divide by 2. Anyone have a number? The 0.05 is 5 times 10 to the minus 2. Yeah, 441 kilonewtons, which is a good fraction of the thrust that the Saturn V rocket produced when it took our astronauts to the moon.
Okay, thank you. Yes, and for part B, would we only consider the weight of 2 cars instead of 45 and just change that in that equation?
So, yeah, so we're going to change the number of cars that we consider. And actually, for part B, I'm going to say, let's do this. And make our system just cars 38 through 45. That way, the tension between 37 and 38 is actually external to our system, so it's coming from outside. So it'll actually show up when we consider Newton's second law. Right? Because then we write down, we do a little diagram for this, and we've got weight. So 38 through 45 is 7 cars worth. And then the only external force in the x direction is whatever the force from car 37 is. Alright, so once again, let's say this is positive x, positive y. And if we write down Newton's second law in the x direction, we just get F37 equals ma. Well, actually, right, mass of 9 cars there. But we actually know everything on the right-hand side. So this is a really, we drew our system boundaries very conveniently, so that what we wanted to find out was on the left-hand side, and everything on the right-hand side we already knew.
Where did the 9 come from again?
Ah, because there's 9 cars in our system. Cars 38, 39, 40, 41, 42, 43, 44, 45.
Oh,
Oop,
I thought you
sorry,
said
that
there
should
were
be
7.
7.
Oh,
Yep. Alright, clearly I need another cup of coffee. That's a pretty good amount of force, being a little piece of steel there. And if you think about it, the further to the front of the train they are, the more force that those couplings have to endure. Right? Because like this coupling here has to endure enough force to pull all 45 cars.
and would we not consider like the friction here because the 7.5 is the friction of the whole system, including the engines and all the trains?
Oh, you know what?
But
You're right. So we should consider that friction. Um, it's not going to change the answer by much, but you're right. There should be some amount of friction. Um, right, so that amount was for all 45 cars. So if we multiply by 7/45, that's the amount of friction that there are for just 7 cars, right? And since I've made 2 under-caffeination mistakes in a row, I'm going to excuse myself for 1 second while I pour a second cup of coffee. I will be right back. Alright, I'm back. Yusuf, no, this problem's not going to be on the test. This is too hard for a test question. Alright. Chapter 5, number 14. Alright. Okay. Maximum acceleration. Alright. Take a snip here.
What threw me off was the part about only considering like 2 drive wheels and sort of using that to like set up the problem.
Okay. So you know, on your car, only 2 of your wheels are actually turned by the engine, right?
Wow, I'm learning so many new things today.
So if you drive a sedan, chances are that your car is a front-wheel drive. That's right, Jolene, unless it's an all-wheel drive. So if you drive like a Jeep or a Hummer, then you've probably got 4-wheel drive. If you drive a sedan, it's almost certainly front-wheel drive. So your engine only actually spins your front wheels. So all of the acceleration from the car is produced only by your front wheels. Okay. So if we're going up a little incline, right? This is our situation where we've got here we're going to ignore rolling friction. That is, we're going to consider the tires that don't slip at all, and it's just the friction between the tires and the surface that is actually propelling your vehicle forward. So, boop. Friction. And of course, we'll also have normal force. We'll have weight. Alright, so far so good? Let's say that up the ramp is the positive x direction, normal force is in the positive y direction. Okay. So when they say that the front wheels of your car support half the weight, what they mean, say this is your car. Your car's weight goes down, right? But then you have normal like your tires are touching the surface in 2 spots. So you actually have a normal force from your front set of tires and a normal force from your back set of tires. So half of the normal force, right, is on each set of tires. So when we go to calculate the static frictional force between your tires and the surface, only half the normal force is going to count toward your front tires. Half of it's going to go to your back tires. So they do say assume that half the weight of the car is supported by the two front drive wheels. If you're on a slope, in reality, like, more of your weight is going to go on your back wheels. If your car was, uniform in its mass distribution. To counterbalance that, actually, most of the weight of your car is in the engine. So generally, your front wheels are supporting more of the weight, in reality, at least if you're going on a flat surface. That's why, when you go to get a tire changed, you might get your tires rotated. So the tires that were in the front get moved to the back. Right? That way you spread the wear out evenly. Did I blow your mind again, Yusuf? All right. Okay, so here's our situation. Let's break down the three vectors that we've got. Friction is going to be just in the x direction, and only the front wheels are going to produce friction that actually moves the car. So there's going to be a factor of a half in there. The normal force is going to be just in the y direction. And the weight is going to be mostly in the y direction. Does anyone need a breakdown of these vectors here? Or are they clear on why we get sine and cosine and everything?
Oh, I understand what we do sine cosine, but how do we know if, like, when we draw our like imaginary triangle, how do we know if it's like if we are going to the right or to the left? Like,
yeah, so that's a really good question. So if here's our weight vector, right? And we need to draw two legs. We need to draw a leg in the x direction and a leg in the y direction. And whichever we draw first, like we start here and we say, all right, let's draw the x leg first. All right, well, that we just went in the negative direction, right? And then we draw in the y leg, and oh, actually we moved in the negative y direction as well. Does that answer your question?
because like when I drew mine, I just did like kind of like so like the wave was like straight down,
Mm-hmm.
and then like the x I just did like going to the right and then going to the up to make like a right triangle.
Oh, so you did one of these instead of tilting it like I drew here.
Yeah.
That's perfectly fine. If you make your x and y horizontal and vertical, that just means you have to do more work breaking up your friction and your normal. But you'll get there the same way.
Okay. Thank you.
Yeah. So actually, let's do it that way as well. So if instead we made our coordinate system like this, then our friction would not just be in the x direction. It would be part in the x direction, part in the y direction. So we'd still have the mu n over 2, but then the part in the x direction would be cosine 4 degrees, and the part in the y direction would be sine. And then our normal force would also be in both the x and the y directions. So our normal force is going like up and to the left. So that's going to be, its x component is going to be negative. Why do we use trig in the red? Because we're pointing our coordinate systems in a different direction, right? So if our x direction is horizontal, our y direction is vertical, that means that our weight goes in exactly the y direction, but our other two forces do not go directly in the x or y directions. So we have to break them down with some trig and triangles. If we rotate our coordinates like we did in the blue and the green over here, then our normal and friction are in the y and x directions respectively, and we only have to use trig to break down mg. Right? So the difference between the green and the red is a matter of perspective. Like, what do we consider the x direction to be? Does that answer your question, Yusuf? Okay. All right. So when we look at these, like, you can see actually why I chose to tilt the coordinate system, because the breakdown in green looks a lot simpler than the breakdown in red. Okay. So let's work on the green over here. In the green, right, we've done our picture, we've done our coordinates, we've done our vector breakdown. It's time for physics. And what should the sum of forces in the y direction be?
0?
Should be 0, yeah. Because we do not expect to sink into the ramp nor to fly off the ramp. And this tells us that the amount of normal force must be equal to mg cosine. If we go to the x direction, now we have mu n over 2 minus mg sine. And what should the sum of forces in the x direction be? Yusuf, remind me never to drive with you. So do we know what the forces should add to in the x direction?
The kinetic friction and the movement, right?
Right, well that's what we have here. But what should they add up to? Should they be 0 or not 0?
I think
Not 0.
Yeah, it should be not 0, because we are actually accelerating up the slope.
Yeah, that makes sense.
In fact, this a, that's what we're looking for. So let's go ahead and solve for that a. And also, I want to take this expression for n that we got from the y direction, plug it in here. So actually, that cancels out all the m's. Got an m in every term. So just divide that out. There we go. There's our acceleration in the x direction. And then we just have to, for A, B, C, we just have to plug in different values of mu.
I have a quick question. For when we did like the MGs, like the vector short MG, how come we didn't do like 1/2 MG sine of like we add how come we didn't add 1/2 to both of them?
I'm not sure I understand.
Like when we do like the MG vectors, how come we didn't do like 1/2 MG sine of 4 and 1/2 MG cos of 4 since like the weight was like 1/2?
Yeah, we took care of the 1/2 up here instead. It would have been perfectly okay to consider the, well, actually no, that if we only considered 1/2 the weight down here, then that would be like we were only considering the acceleration of half the car. But it's not half the car we want to analyze. It's we just know that we only the friction from the front tires is going to accelerate us. Ziki asks if we did it in the red way, would we get the same the same formula? Let's do it in the red way.
Quickly before we do that, for the green part, where did the it was originally UN/2. Where did that go when we plugged in MT?
You are 100% right.
Also, would a question like this be on the test?
There will 100% there will be a box on a ramp question on the test. I don't think it'll be this complicated, though, this sophisticated. It'll be a simpler box on a ramp question. In fact, there will probably be 2 box on a ramp questions on the test.
Okay, thank you.
Yep. So in the red perspective, so we come down here, sum of forces in the y direction now is equal to mu n/2 sine 4 plus n cosine 4 equals, it's going to be 0 or not 0?
Zero.
No, it's going to be not 0. We're going up the ramp, which means we are actually accelerating in the y direction. Not much, because it's just the sine of 4, but it's there. And then if we write this down for the x direction, oh, I totally forgot the weight in that previous one. So we get 2 sets of equations here. They're not very convenient. In the green perspective, when we looked at the y direction, we actually had an equation of only one variable. There was only normal force that we did not know. So we were able to solve for it. In the red perspective, we have both of our unknowns, n and a in both of our equations. That makes it more difficult to solve. So we'll have to do some solving. We'll have to solve for n in one of the equations, plug it in the other one, and that'll give us an expression for a. So a little bit more complicated algebraically. Oh, have a good day, Selena. Yeah, Yusuf, that does sound awful. It's not impossible, and we'll get the same answer. But we will have sweated and bled more than we had to get there. So if we took the x direction, maybe factored out an n from the two terms on the left here, we could get n times mu cosine 4 over 2 minus sine 4 equals ma cosine 4, and then solve for n. And then take this thing, plug it in here, solve for a. You could do that. You're going to have to distribute anyway, so it's not going to save you a whole lot of trouble. But yeah, you could factor the n out before you plug in. The other possibility would be maybe to solve both of these equations for n, and then set those expressions equal to each other. Right, so you'd have, so this is our expression from the x direction, then we'd have an expression from the y direction that looked something like ma sine 4 plus mg over, let's see, there's going to be mu over 2 sine 4 plus cosine 4. Yeah, that looks pretty bad. Oh, the one in green is done. Alright, so let's not do the red version. And for question 15, it asks for all four wheels. Yeah, it upgrades you to a Jeep, so you got four-wheel drive. And yeah, you would just take away this factor of a half in the friction. Yeah, so the red one, that's what happens if you don't rotate your coordinate systems. You get something that's, solvable in principle, but challenging. Yeah, challenging. Huge time waster on a test. Yes. Yes. All right. we have some more questions that we want to look at?
Someone accidentally sent me a problem. It's chapter 322.
322. Farmer wants to fence off his four-sided plot of land. I feel like we did this one on Saturday. But maybe I'm crazy. Did we do this one on Saturday, guys? People who were there? Oh, we did the three-sided version of it, the triangular one. All right. Okay, so this is a chance to practice some vector addition. Where the idea here is if we start at, say, this corner here, and we take our journey along the A side, and then along the B side, then along the C side, then along the D side, we end up back where we started. So that's what they mean by A plus B plus C plus D equals 0. So in this problem, they were nice enough to draw a picture for us, and we're going to go ahead and call east the positive x direction and north the positive y direction, which is implied by their picture. Does graphical versus analytical matter on the test? Yes, I will not ask you to do graphical analysis. I know I can't draw for crap. I don't expect you all to draw for crap. But I do expect you to be able to do algebra and trig. So yeah, there will be no graphical analysis. That's the fact that we even mention that at all is a holdover from the days where we didn't have plentiful computing, right? Where protractors and rulers were more common than supercomputers, but these days we all carry supercomputers in our pockets. And we don't carry protractors at all, generally. All right, so let's break down these vectors. Oh yeah, if you actually need a protractor, you can just download an app for that. All right. So what does the component form of A look like? So for A here, the angle we're given, this 7.5, we would make an X leg and a Y leg. And the X leg is adjacent to this angle. So that'll be cosine. And the Y will be opposite of that angle, so we'll use sine. Also, I don't know why I put 4.75. We're here, we put a negative sign on the Y part because it's going to the south. Then B B is going to be is pointing in quadrant 2, right? It's going up and to the left, or north and to the west. So it's going to have a positive y component and a negative x component. And the x component is actually opposite from the angle we're given, right? Oop. Right, so this 16 degrees is opposite our west-east axis. So we have minus 2.48, and then we'll have positive y. C direction. The x leg of our c vector is adjacent to that 19-degree angle, and it's still in quadrant 2, right, to the west and north. So we're still going to have a negative x part. Okay. And then we have D. And we don't know anything about D. Except that the reference angle we're given is adjacent to the y leg of the D triangle, so we will have sine theta in our x direction, we'll have cosine theta in our y direction. We can see that D is pointed into quadrant 3, so they're both going to be negative. And then we'll just call this hypotenuse D. There we go. All right, is everyone with me so far? All right. Okay. So we can't attack D directly, but we can maybe sum up these three things. So let's say A plus B plus C equals R. And to add up these bits, right, we're just going to add up the x components of A, B, and C. That'll be the x component of R. And we'll add up the y components of A, B, and C. That'll be the y component of R. So I get something like 1.12. Let me double check that. That doesn't seem right. Yeah, that's right. This picture is just drawn misleadingly. Oh, well, actually, no. What it is we actually called this thing over here the origin. Okay. So after we've gone through sides A, B, and C, We've gone a net 1.1 kilometers in the x direction. Yeah, so the we started our journey at the beginning of A, like the intersection of A and D here. So relative to this beginning, we've gone 1.1 in the x direction. Yep, 2.8 in the y direction. Agreed. Was there a question?
So since this is like not like a triangle, we don't have to do like the square root of like a square plus b square. Like since it's like four sides, we can just add the x and then add all the y's.
Well, so here's our basic plan. So our idea is, so first we break into x, y components. And then we sum up all of those x and y components. And then we use the Pythagorean theorem to get the length. So then, right, we do something like that, right? So to be able to do any other sort of arithmetic with vectors, we have to break them down into x and y components first. Once we've got them in x and y components, then we can add them, subtract them, do whatever we like to them. And once we've finished doing whatever it is we need to them, then we can use the Pythagorean theorem to go back to length of a vector from components. Does that answer your question?
Yes, thank you.
Okay. All right, so this is our R, and given our original statement that if we sum up all four of these vectors, we should get 0. Well, now we can say, well, R plus D should equal 0. So R plus D is going to be 1.1 minus D sine theta in the x direction, and it'll be 2.8 minus D cosine theta in the y direction, and it's going to equal 0, 0. So this gives us two unknowns, D and theta, but also two equations, like one for the x direction, one for the y direction. Right, so we have something like 1.1 over sine theta equals D. That's from the x direction. And then we can plug that into the y direction and get like 2.8 equals D cosine theta equals 11 . Why did I put cosine theta in the bottom? Right, running out of room a little bit. Gonna come to this top right corner to finish it off. Right, so cosine over sine is cotangent, Or another way of saying this is this right-hand side of the equation is actually 11 over tangent. So 2.8 equals 11 over tan theta. So tan theta is equal to 11 over 2.8. And theta is equal to arctan of 11 over 2.8. Not 11, 1.1. A victim of my own handwriting. $76 sounds right. Actually, I get 21 degrees. You are also a victim of my penmanship. That's why I'm going to type the exam questions.
I actually have a question really kind of similar to this one, which is for the lab. We're given a graph like this, and we have two components, and you can see that the y is not straight on the y, but it's tilted. How do we get the resultant for something like this? Because I thought the resultant is usually in the middle between the two,
Between
right?
wait. So when you're adding two vectors?
Yeah, so we're attempting to add these two vectors. Where would the resultant go? Here?
I don't see what you are. I can't see. My eyes are not good enough, and the video
It's
is too
just like
small.
it's just two different forces. So it's just F1 on the x-axis and F2 at a 60-degree angle.
Yeah.
That's
So
all.
so graphically, if we're adding vectors, right? If we were just doing a plus b in this on this graph here. So if we draw a, and then we draw b starting from the tip of a, and then a plus b is from the tail of a to the tip of b.
What if they both have heads? Like the heads are heading in the same direction. I don't know if that makes sense.
So if you, it does. So let me. I think I know what you're asking. Let me finish this off real quick, and then we will talk about that for sure. Okay. So, if I am hearing you correctly, you're saying that A is like this, right? And then B is like this.
Exactly. Yeah.
Okay. If you draw them like this, you can't visually estimate what it should be. Right? What you have to do is you have to draw A and then start B from the tip of A. And then the sum is from here to here.
I get it. Okay, and then that would mean for A that the y is 0, right? Because it's on the x-axis.
Correct.
Perfect. Thank you.
With any questions? Oh, that's not the one. This. Any questions on this problem before we move on? Anybody? how does gravity affect horizontal displacement? You're talking about the lab where, if you had the ballistic lab, right?
I think so. It was like projectile motion, basically.
Yeah. If you were in person, that's a super fun, although very loud lab to do in person.
Wow, that sounds fun. I'm glad to know we missed out on it.
I mean, there are some really fun labs in this class. It really makes me sad that you don't get to do them hands-on. But yeah, so gravity does not directly affect, or does not affect horizontal speed. However,
Right.
gravity does affect your hang time, right? The time that you're in the air.
Okay.
So more time in the air means more horizontal displacement.
I put that, but I used my explanation was just like rearranging a bunch of formulas to demonstrate that. I don't know if that works as well.
That probably works. I mean, I don't know who your TA is, but that seems completely reasonable.
My TA is a very strict grader.
Who is it?
Chung.
Tang Chun?
Chung.
Chung. I know the guy. He is in fact a very strict grader. Your impression is correct.
But thanks for answering my question.
You're welcome. Do we have anything else today, or is it time for me to go brew another pot of coffee? 'Cause you know what they say.
I actually had another question about like the vectors on the test.
Sure.
So is it always going to be like the same format for how you want us to sort of like show the vectors, or could we also use stuff like tables or like
So, yeah, so if you wanted, there are a few, so I obviously have my preferred way of writing vectors, right? I prefer to write vector like so. If you don't like that, that's fine. You could also do something like a table. That's fine. You could also use unit vectors. Any relatively standard way of writing down vectors is fine, as long as I can tell what you're talking about.
Okay. And in terms of like the coordinate system, does it always have like an origin that we write somewhere, or?
So, if we're doing kinematics, then the origin matters. If we're doing a sum of forces, origin doesn't matter so much, right? Because when we're doing a sum of forces, like we're not going anywhere. We're just trying to analyze how we'd accelerate if we were going somewhere.
Okay.
Does that make sense?
Yeah.
All right, we've got a request for chapter 3, number 28. All right. Daredevil is trying to jump his motorcycle over a line of buses. Some Evel Knievel stuff right here. I don't recommend you try this in person, but if you do, make sure to invite me. Alright. So we've got a ramp. Like so. And then we've got some buses. Right? Possibly several of them. And we've got a crazy person on a motorcycle. God, that really looks like a bicycle. Well, I'm going to call it good. Anyway. The ramp is angled at 32 degrees. The buses are all 20 meters long. The initial velocity is 40 meters a second. And because he was going up the ramp, right, this initial velocity is also at 32 degrees. Okay. Do the good old right and up for coordinate system. And since this ramp and the edge of the first bus are supposed to be aligned, we can go ahead and call this the origin here. Okay. So again, in kinematics, there's 4 vectors we're usually interested in. Acceleration, initial velocity, initial position, final position. So what's acceleration in this case? Don't everybody answer at once. Yeah, you two are exactly correct. It's nothing in the x direction. It's minus g in the y direction. What's our initial initial velocity?
Is it gonna be 40 cos of 32?
That's exactly right. Initial position? Right, let's start this analysis right at the point where he leaves the ramp, at which point his coordinates will be basically 0, 0. And for final position, we don't know where he will be in the x direction, like how far he'll have gone in the x direction. But the y should be 0, because we're interested in how far he's gone when he crosses the level of the height of the buses. Right? He'll hit the ground at some other point over here. We also don't know how long this is going to take. So if we do a quick check, we've got two unknowns, t and x. But we know that we can write down two equations using our first kinematic, so we're not overly worried about this situation. All right, so in fact, let's bust out that first kinematic. In the x direction, this is essentially x equals initial x position is 0, initial x velocity is 40 cosine 32, and acceleration in the x direction is 0. In the y direction, we're looking at final position of 0, initial position of 0, Jolyn, chapter 432 next? Yeah, we can do 432 next. All right, so we've got these two equations, two unknowns. Which direction should we work on first? The x direction or the y direction? What seems simpler? Yeah, totally the y direction. Because in the y direction, we've only got one variable. So we can totally solve for that. In fact, we don't even have to use the quadratic formula, because we get 0 equals, right? We've got a t in both of these surviving terms. So we can factor out a t. So we're going to have two solutions, right? So one solution is if t is 0, right? And so yeah, your bike is at height 0 if you are at the top of the ramp at t0. So that's definitely true, but it's not the one we're looking for. The one we're looking for is the solution implied by the parentheses. So if this parenthetical bit is 0, that implies that 40 times sine 32 divided by 5 is t. All right, so with that in hand, we can actually go back up to the x direction and say that, well, then x is 40 cos 32 times 4.24. Anyone have a number? 144. Yep. That's a lot. If the buses are each 20 meters long, this is about 7 buses with 4 meters to spare. Alright, so that actually gives us the answer to part B as well. So our margin of error is about 4 meters, which I think is like a fine margin of error. It's relatively safe. Any questions or comments about this one before we go to the next?
So whenever they give us like a velocity and there's like a ramp, then we always have to include that like that degree in when finding velocity, the vectors for velocity.
Yeah, so our idea is that if we're traveling on the ramp, then when we get to the edge of the ramp, our velocity ought to be in the same direction as the surface of the ramp. Does that make sense?
Yeah, so like for example, like it's not on a ramp, then it says like, oh, someone hit the ball at this velocity, then we just use that velocity without taking into consideration like the height or anything like that.
Um, I mean, I feel like this is too general a question to make a rule on.
Okay.
But yeah, we should definitely always be aware of what our angle is. So even if we're not given an angle, maybe we have to solve for the angle, right? So it's something we should always definitely be wary of.
Oh, okay. Thank you.
You're welcome. All right, and then we have Jolynn's request. So suppose your car was stuck in the mud, and you wanted to use this method to try and pull it out. So it does seem to me that there are maybe better ways to pull your car out of the mud, but what do I know? So the idea here is that you've got a cable stretching from your car to a tree, and then you've got someone pulling on the something pulling on the middle of the cable. Okay. So let's actually redraw this a little bit bigger so that we can tell what's going on. We've got car, we've got tree, and if we just tied the cable between them, right? The cable would take a straight distance. But we're pulling on the cable somehow, maybe with another car, and so the cable is bent. Right, because we're pulling on it with some force. In fact, I'm just going to call this P for pulling. And then we make an angle here, right? We pull at a certain certain number of degrees out of true with that force. All right. So we're going to go ahead and call right the positive x direction and up the positive y direction. We're going to note that this cable is got to the mute button in time. Thank you. This cable is essentially divided up into two pieces. There's going to be a tension T1 on this side. There's going to be a tension T2 on this side. Okay. So first question, what force do we have to exert? Like, so how big does P have to be in order to exert 1200 newtons of force on the car? That is, T1 is 1200 newtons. Let's do a little vector breakdown here. So T1 is going to be, right, in the x direction, the x leg of T1 here is going to be parallel to the x direction, or sorry, is going to be adjacent to the angle here. And it's going to the right, so it's going to be positive. And we're told the angle is exactly 2 degrees in this case. So cosine 2. And the y direction is going to be negative. T2 is going to be real similar, except it's pointing to the left and down. That'll be negative in the x direction and negative in the y direction. I actually want to be careful about the directions of T1 and T2. So the way I wrote them down here is actually the way I drew them in the figure here, but that's the direction the tension is going to be pointing in the cable at the car and at the tree stump. Right? That's two separate locations, right? And when we apply Newton's second law, we can only apply it on one location at a time. So we actually have to be careful and decide which location are we going to be applying Newton's second law at. Are we going to be applying it at the car, at this point here where P is applied, or at the tree stump? Julien says P. Yeah, I agree. Like we should apply it at point B. If that's the case though, at point P, tension 1 is not pointing down and to the right, it's pointing up and to the left. And T2 is not pointing down and to the left, it's pointing up and to the right. So we should actually have these all reversed. All right. And then lastly, we have our pulling force, which is only going to be in the y direction. All right. So if we're going to apply Newton's second law at the point where P is applied, let's start with the y direction. Actually, let's maybe start with the x direction. So the sum of forces in the x direction will be T2 cosine 2 minus T1 cosine 2. Yeah, so Yusuf, you could think of this as specifying the origin for a force problem. That is true. So in a lot of the force problems that we do in chapter 4 and 5, the point at which the forces are applied is going to be obvious. It's going to be the box that's on our ramp, or it's going to be the sled that a kid is pulling, or what have you. In this case, it's not obvious where we should look at. And in fact, if we're not explicit about what point we're analyzing, we're going to get nonsense out, right? So yes, you could definitely think of this as specifying the origin for a force problem. So sum of forces in the x direction. Do we expect that to be 0 or not 0?
What I'm thinking is not 0, so that we actually move the car out, right? Because if it's 0, then we're stationary, and we're trying to get the car out.
That's true. We're not given any information about the car's movement, right? Like, we're not told that 1200 newtons is enough to move the car, just that we want to see if we can apply 1200 newtons of force. Does that make sense?
So kind of like, yeah, testing whether the force is appropriate in a way.
Right. But even beyond that, even if the car was moving, right? If we're pulling this point down, right? Is that point on the rope, is it going to move left or right? Or is it only going to move down?
I see it now. Yeah, so it should be, it should equal 0 on the x, but not the y.
But yeah, maybe not the y if the car is actually moving after we tug on it. But in the x direction, definitely should sum to 0. In which case our cosine 2's can cancel out. And this tells us that T1 equals T2. So the quantity of force in each half of the cable is the same. And then we look at the y direction. And we do have to play a bit of a game to think about whether this sum of forces should be 0 or not 0. If this force is enough to move the car, and then the car will start to move. But if the car starts to move, our angle is going to change. Right? So we want to kind of think about this. Well, at the moment that the angle, So we want to think about this in sense like the angle that the rope makes is 2 degrees, and the car hasn't started moving yet. Right? So so that anyway, that's a fancy way of justifying that sum of forces in the y direction is also 0. Okay. And here we know everything on the right hand side. So we want that tension to be 1200 or 12,000. So I guess pulling perpendicularly on this rope is actually not such a bad force multiplier, right? Like you exert 1600 newtons of force, and you end up pulling on your car with 12,000 newtons of force. I think you might have forgotten this too, Yusuf. Or maybe... Oh, no. I put an extra factor of 2 in it. This should be 837. That's even more impressive. You put 837 newtons in, you get 12,000 newtons out. Right? 830 newtons of force is a significant amount for a person, but it's an amount of force that a person could exert. Where is all of this force? So if we're supplying some force in the y direction, where is this force in the x direction coming from? Right? How is it we can pull in the y direction and yet the car moves in the x direction?
Is it coming from the cable kind of wanting to regain its shape?
Yes.
It was called reformation or something like that.
Yep, that's part of it. That's part of it. You're close, because there's actually one other thing beside us that is tugging on this cable. The tree. Right? So the tree is pulling in the x direction. Okay, so part B in this question actually asks about the part of chapter 5 we haven't covered yet. That's right, Yusuf. It is stationary, but it has to exert force to remain stationary because the rope is pulling on it.
It kind of like, when you drive, when you start driving, your body kind of goes back to keep you stationary, right? So it's kind of like exerting an equal but opposite force.
Yeah, so in this case, it's actually the back of your seat that is accelerating you forward. Right? So your car accelerates your chair accelerates you.
Yes.
This is more like, imagine you were imagine that you're using a wall to like stretch your calf after you're jogging, right? You're pushing back on your calf to kind of stretch it out, right? So if you're pushing back on the road, that means the road's pushing forward on you. What's keeping you from falling over? And it's the force exerted by the wall, right? So you're exerting a force on the wall. The wall doesn't want to move, and so it exerts a force back. Do you feel satisfied with this question, Jolene?
Thank you so much. Yeah.
You're welcome. All right. So I think that's about it for today. You all have asked some really nice questions today, both which proves to me that you're doing problems from the book, which is amazing. But you're also asking pointed questions about why things are, which proves to me that you've been thinking deeply about this. And that's very gratifying to see from a group of students. So yeah, I take my hat off to all of you, if I were wearing a hat.
So much for your time. Have a great day.
You as well. I'll see you all Friday.
Sorry, really quick. So the exam is going to be posted under a module or something for us to access?
There'll be an announcement
Okay.
that gives a link to a Google Doc.
Oh, okay. Thank you so much.
Yeah.
All right. Bye.
Bye.